अभी तो यहाँ पे 7 आ रही थी, अभी 4 आ रही आपकी वाली अपना इधर बैठे और इस मॉडल से तो बात है USB
Esteemed guests, distinguished faculty members, dear students, and all participants present here today. It is now my proud privilege to invite the highlight of today's event, our esteemed keynote speaker. We are indeed fortunate to have with us a scholar of exceptional stature whose contributions to the field of computer science in IIT have left an indelible mark on both academia and research. A visionary academician, a prolific researcher, and a mentor of excellence. He has guided generations of the students and researchers towards excellence. Please put your hands together for a gentleman who needs no introduction, but the protocol demands that we do justice to his remarkable journey. Professor D.K. Kilovial, Professor School of Science, Computer and Physical Sciences, Jawaharlal University, New Delhi. A little more introduction. Okay, and I also welcome session chairs, Professor Dr. Jyotish Malhotra and Professor Mohit. Okay, sir.
That's what you want to say, and then but that seems to be that's right. And let us see what I'm going to talk about is I have read some books and based on that knowledge gain. I try to read that as it's not downloaded from that's what it is. So let me put you through idea what when I say because I feel like for the AI and machine learning, yes, wonderful, but also it's misused or abused or overplayed. That's what I see. Even if you try that, it can do what it cannot do. That's what limits me. But it doesn't mean that the limit is just beyond be done. Probably for the time being, it is not just about but how much. That's always the question. That's what I put to my level. Let me go back now. If you can this, what I'm trying to say, when you talk of deep deep learning and details of machine learning. One of the important points is, if you look at it from the multi-layer perspective, it is started because of the non-linearity of the functions which are, that's what the background of the. And what is important, had there not been any research that on the mathematics or approximation of functions, probably this multi-layer perspective might not come down. That's what the whole idea is. So the research of the mathematics on function approximation has led to the development of multi-layer perception, and especially the knowledge functions. So this is what I am trying to say. I'm not going to run the pipeline and take a device from the pattern of the So that's what machine learning issues that I see in practice. Yes, for the area which are not computer science, those who are not applications of machine learning, they will run the library, they will take the data, but those who are not computer science, they do the same. Then what is the distinction between those who are doing research in computer science and those who are doing research in non-computer science here? If you do the whole Python library and data sets from somewhere, run some algorithm, no incremental addition to any other theory of yours. That's what I'm trying to say. That is where we must try to distinguish between computer science and other sciences. That's what computer science is. That's what I said. And then we understand the nuances. How it has come out, we will not make any difference in the, that's how the science is concerned. So what I said, that approximation is very important. Second is, if you know differential calculus, the chain rule is very important. If I have to find dy by dx of ux and vx, then or more multiplication, then the chain rule was important. See, this chain rule, what people are introduced is the mathematics that has also helped evolution of neural network. Why? Had there not been the chain rule of differential calculus, that approach is could not have been possible. Look at how important the mathematical background for entire machine learning is. And backpropagation, if you look at it, in 60s when it came that already have the structure for neural network is one of the areas backpropagation development, and that is because of the chain rule in mathematics. That's how it was after 90s. And then that led to a lot of developments and deep learning what we call it became after 2006. And earlier machine learning were used with different names. In 40s, 50s it started with cybernetics. Then it started with the connectionism when they tried to connect various layers with connectionism. And now after 90s or some people start calling machine learning. That's how. And 2006 on deep learning and so on. If you look at it, see why I am putting focus on the neural network is the region. Even if you use the CNN, RNN, or encoder, decoder, wherever you go, or in fact generating AI, all is depending on the neural network. The basis is neural network. That's what. So it's the important point what I am trying to make here is the challenge, if you look for the neural network, how the performance of neural network improved. If you look at that, one of the reasons it improved is so the primary aim is statistical generalization that I will talk about does it mean. And to do that, earlier the data sets were larger, and the larger data sets came. The statistical challenge of generalization was overcome by the larger data sets. That is one of the development which improved the performance of neural network. The other issue was that not only the larger data sets, the model complexity also increases with the time. That is another what you call development in the neural network. Not only that, if you look at the hardware level, at the GPU and other things not have come, probably we have not been able to run the larger neural networks. That was other development and the software. However, it is not sufficient that the hardware and software change has only brought or improved the performance of neural network. Part is small algorithmic changes which took place that has also improved the performance of neural network. What are those algorithmic changes? That's what one of the important points. These changes are, if you look at all of you do mixed parallel, right? Y minus fx of whole square and summation over n. That's how we go. And this is not the only way of minimization of error. Another development is to place it across entropy. And the concept of cross entropy has not been designed, or what you call KL emergence has not come. Probably we still have been breathing the meaning square. That was another development which improved the performance of the result. And that is how to solve this. The solution of the solution was the maximum likelihood algorithm. That I'm trying to find out the argument will give you the maximum value and output of the result. So the maximum likelihood algorithm was one of the solutions for finding the minimizing the error. For finding the what you call optimal value of the parameter. Second is, another development came. Every time you go for integrating fusion, let's say citywide function was a very popular function in Indian network application. If you look at all these networks, if you look at the hidden layers, most of them is available. Hidden layers is available. Why available function? That is very important. And the replacement of sigmoid value, which gave a piecewise linearity as a basic function. When I say piecewise linearity, if you look at value, what kind of negative values of 0 and then it's a linear function. A linear function is optimized. That also is important. So that also gave a rise to the performance improvement, but never gave sufficient. The future performance will improve if you have some advantage in the optimization. That's very important. Still, when you do optimization in neural network, the problem is you don't find the optimal parameters here. Well, many of the algorithms, they try to optimize, they either stuck in the local minimization or in some rift or some reach, some saddle points, and probably not global winning. That's the problem. That's all of it. Now, what do you do? We try not able to get the parameters in the deep. So still, we try to get a value of parameters. That is best in that obligation. But that is not optimal. So it's still finding an optimizing problem. That complex function is able to get the global minimum. So that is what there is a lot of and not all the models or models we design, they are not yet sufficient. There is still scope for improvement in that model. That's all. So two areas in future research with this detailed study of optimization and modeling. Can really continue the scientists to the area, not simply running pattern life. That's the idea which I want in short. And secondly, and skip this. Let me talk the point what I want to say. What we are trying to do, look at this. Let's skip some slides. Given any data set. This is the important if you understand machine learning. See, we read this algorithm. Yes, we read lot of algorithms. But you have to understand the corrections. That's the point I will make in the short time. See, I don't any data points. There's some function, whatever we fit to the data points. But knowing it is difficult. I don't know which function will fit. But function is complex. Right? Some function will fit to that. Let us call that effects. Right? We assume that the function fit to the data points. That it will be able to clearly classify. But we don't know that function. That's the difficulty. Then how to start it? Had I been knowing the function, the machine learning खत्म कर उसी function को लगाता, तुरंत classify कर देता ना, it would have been able to classify immediately if I apply that function. But I do not know that function. So what I have to do, I have to start from the function. my assumption. And how do you know that this HX will fit? That's actually that I thought. So what I mean, what I might be, okay. So now idea is I will start with some HX which I should assume that this is probably trying to classify, right? And then I try to see how the HX approximates. But I don't know what HX how do you say that how HX should affect. That's what I'm reminded. And we will affect HX. That's what you are doing. So if you say the HX, you try to apply HX, then it will give you some error. And I try to minimize that error, make sure that you try to minimize that error. Why was I trying to minimize that error? Minimum error that is HX for problem. That's what I'm doing. Right? And these ideal errors which you are HX affects, but that will not happen. So the whole idea is, this idea, that's what you are doing. See, I minimize that, I don't know. Now, what does it mean now? This is what I think. This is the most important equation to understand that my ideas. In a short period, I can know. So I have a and node. What is node to me? Node to me is data and HX. दो एक चीज पता है, डेटा पता है, लेबल्स पता है, इनपुट्स पता है, and then HX पता है. So that is I know why. Label is why. I know why. And I have HX. If I apply X to the data input point X, I get some point. Right? So what I'm trying to say, wait, I'm not HX to the input. I might get some output which is identified. Therefore, difference is the label I have given and also I manage by HX. So therefore, difference. So why HX? This difference is there. Since I know why. So what I approximately with HX means I try to approximately by getting the difference or minimizing my difference between Y and HX. Right? That's what I mean. Already done. Look at these here points. This is total error. I have three things here. One. If you ask for Y minus FX, that was if I find the exact FX. And if it will give me some output. I need that output. Why? But when I measure my labels, I have measured that the labels my not जब आपने आउटपुट मेजर किया तो उसमें सारा मेजरमेंट के नंबर किया so this why not react so therefore many kinds of exact function and apply exact I get output that output will not be same as y. So there is a difference between the actual output and the observed output. Right? That's what the y minus x. Second term is I have function which I want to affect and then the difference between affect and what is affect? The moment I say after that linear regression by linear regression after that 0 plus W1 x plus W2 x not करना है W1 x the moment what is the right any number of operations see this linear expression of n variables may have multiple values so that I have some support for if I say one and one plus 2 x plus 2 x to the some so multiple functions what is the value of parameter right which one is correct और वहाँ पे polynomial जो y equal to mx plus c so it may be 2x plus 3 it may be 4x plus 5 it may be 7x plus 8 which one is correct you choose only one. So what I am saying is that the experiment which you are choosing is out of the multiple possible functions, there is one function. It can be estimated as x. I choose that. Again, it's a number. Now, when I am choosing this one, x, then how do I deviate from rest of the x? When I want to check something do I check something उसका बाकी कितना deviate of x? That's the question. That is why x minus x is the deviation between the value of x can be how much it deviates from x. And then, if I have chosen for x, then how it is far away from x? But I don't know that x is but x also has that meaning. So what is happening? My total error is consisting of variables. One, the average value of x minus x square. Second is fx minus x square, and third is y minus x. What are these three variables? If you look at this, that are all struggle all the time to understand. Right? That's the most finally we struggle to define these three terms. Right? And if you look at my total error consists of three parts. Noise, the last one is noise. But the labels which I have measured are not directly measured all the time, some of them are measured. And how they are far away from actual functions, that gives me the noise in the data. And the second what I say, how the function which I have chosen, estimated function HFX, how it is deviating or far away from or closer to the x. That is my bias. And nothing bias for. अगर ये अच्छा function का कितना करेंगे, and the first thing, I said how much HF deviates from HFX in my values. Now, what happens? When you try to minimize error, you have to minimize either all three or one of them. So most of the time, I said data sampling AI means I am trying to improve the quality of data. The moment I improve the quality of data, I am trying to reduce my error in the labels, noise. Right? So the labels error कम होगा तो noise इतना नहीं होगा. Label data की quality अच्छी होगी, तो ये last वाला part minimize हो गया. तो भी आपके error minimize होगी. And second, you try to also minimize variance and also minimize bias. But do you put any effort on that? हम तो total error ही minimize करते हैं, हमें पता ही नहीं क्या है. Now the question is, okay, I take that. Okay. So when you choose a model, after the metrics, the model has a capacity, how much data point you can classify correctly, how much you can correctly classify. अगर आपने linear equation भी ले ली या कोई polynomial ले लिया डिग्री से, I take a polynomial of degree. It may be categorizing some points correctly and some points you will not be able to correct. And then, how much data is able to characterize? Even if you take any polynomial of degree, if I take polynomial degree, then it will not be classified degree, right? But when I take some particular value of parameters, then it will not be able to classify some of the points. So that is how much capacity a model has to classify. Then, if the capacity of the model is low, then it will not be able to classify some of the points, to choose them. If the capacity of the model is high, it will classify those points which are not classified. That's what it will happen, right? That is what I am saying is, so the model with insufficient capacity are unable to solve complex tasks. That's where the problem. So I need a model with sufficient capacity. And so therefore what happens is, that capacity can be further reduced, it's called representative capacity of the model. Then if I say I have a polynomial function which will classify my points, that's what a polynomial function can classify. If I take exponential, it will classify. But the question is, polynomial will be. The moment you choose a degree of polynomial, then it reduces the whole capacity. Polynomial का बहुत ज़्यादा capacity है. It may be degree of n. The moment you choose a polynomial of 4 degree, then further capacity will reduce. And that capacity is called a representative capacity. That is the model which you have actually chosen will further reduce the capacity of the model, and that's the representative capacity. But that is not sufficient. If you look at further, the effective capacity is lower. How is it? Because any machine learning model will try to get the value of the parameters by applying optimization. What is the quality of the optimization algorithm? How does it optimize? If there is imperfection in the optimization algorithm, then your capacity will further reduce. That is what exactly the effective capacity. So, model capacity, the representative capacity, the effective capacity is even lower because you can apply different kinds of protocols. So if you look at, this is where we are able to define what is overfitting and underfitting. That's what I thought. Let us understand that. When I put a model with the insufficient capacity, then it will underfit. That means some of the points which have been classified as a positive class will be not classified. It will be left out. That's what underfitting means. When I choose a function which even classifying those points which should not have been classified, then it goes over.